I'm going to start the lecture now, and it's about diagonalization and similarity transformation. And this is only the short lecture today, so for 1 hour, and then you're on your own with the interesting exercises in the classroom. Let me just start here. So this is the headline today, and I'm going to start by introducing similar matrices. And then I'm going to discuss when is diagonalization possible. And then I will discuss algebraic multiplicity, and this is called algebraic multiplicity of a given eigenvalue, and also geometric multiplicity. And this is denoted geometric multiplicity. And I'm going to state 6 theorems. I'm going to do 4 examples. And in the examples, I will use 3 by 3 matrices. In your exercises, you will work mostly with 2 by 2 matrices, and you have to do it by hand. So it's okay when it's only 2 by 2. So let me start by giving you a definition, and this is definition 14.1 in the e-notes, and it's the definition of similar matrices. So we say that A is similar to B, and remember we are talking about square matrices, and it is similar if a regular matrix, we call it M, exists such that B is equal to the inverse of M, and since M is regular, you can compute the inverse times A times M. And this looks a lot like what we discussed last Wednesday, and we did that in terms of a mapping and a mapping matrix in an eigenbasis. And remember that we had this mapping, and this is since it's a mapping in the eigenbasis, it's a diagonal matrix with the eigenvalues in the diagonal, and it was equal to this change of base matrix times the ordinary mapping matrix, or in the ordinary basis, and then times this change of base matrix. And this is simply the inverse of this one. It's okay. What we can say now is that if A and B has the same eigenvalues, or have the same eigenvalues, with the same algebraic multiplicity and geometric multiplicity, then you can then they can be similar. And you have that f of me is, this is the linear mapping that you're looking at. Now, if A is similar to B, then B is similar to A. Why is that? I can write it down. If A similar to B, then B is similar to A. You can see that if you have B is equal to this, then you can pre-multiply by M and post-multiply by the inverse of M, and then you get M times B M times B times M inverse, and this will give you M times M inverse times A, and then M times M inverse, and this is the identity matrix, so this is simply A. So this operation here works both ways. But also, if you have that let's say if A is similar to B and B is similar to C, then A is similar to C. And you're going to work with that in exercise 5, question 1 today. So look at it. Now, if A so A can be diagonalized. And what does that mean? It means that it's the same thing as A is similar to a diagonal matrix. And we saw it the last time you had this diagonal matrix, and then you had the set or the coordinate matrix of the eigenvectors, and you could write it in that way. This was, say, version 1, and you could do it the other way round. That is, you pre-multiply this by the matrix V, and post-multiply it by the inverse of V, and then you get that this is V times this diagonal matrix, and this is version 2. So now I'm going to give you the first theorem. And this is, I call it theorem 1. In the e-notes, it's 14.7. Some of the theorems that I'm going to show to you today is not directly given in the e-notes, but it is somewhere in the text. A can be diagonalized if and only if it has n linearly independent eigenvectors. I denote them V1, V2, and up to Vn. And they are corresponding to n eigenvalues. Now, these eigenvalues need not be different. Some of them might be the same for these eigenvectors here, but the important thing is that you have n linearly independent eigenvectors. Eigenvalues. I write here not necessarily different. And I name them lambda 1, lambda 2, and lambda n. Now, in terms of these two equations, then the matrix is simply the eigenvectors as columns, and this diagonal matrix here is the diagonal matrix where you have, say, lambda 1, lambda 2, and lambda n in the diagonal. This was the first theorem. Let me take the second theorem here. Eigenvectors corresponding to different eigenvalues are linearly independent. And you have, in fact, proved this result yourself. If you did the exercises last Wednesday, it was exercise 8. And if not, then please consult it and do it. So let's take an example. And I'm looking at this matrix here. So my A is 1, minus 4, 0, 1, minus 4, 0, and 0, 0, 2. Now, this is, yeah, I could ask you, is 0 an eigenvalue of this matrix here? Yeah? The thing is that if you're looking at the eigenvalue problem, which looks like this, then you can always have the the 0 vector as a solution to this one. And this means that you can put anything here. And we discussed it the last time. If you put in the eigenvalue 0 to see if it is actually an eigenvalue, then you get the 0 vector on the right-hand side, and then the solution to that problem would be the kernel of A. But this is not interesting if the kernel has a dimension 0, if there's only the 0 vector in the kernel. The 0 vector is of course always a solution if you have 0 on the right-hand side, but it would be interesting if there were other solutions to that problem. And is there other solutions to that problem in this case? There wouldn't be other solution if the matrix was regular. Because if it was regular, then you had the inverse of this matrix, and you can pre-multiply by this, and then you would get the solution. That is, if you have a tends to be equal to 0, if lambda was equal to 0, and then you multiply with the inverse of a on both sides, and you get equal to 0. This is the identity matrix, so you will find out that you only had the 0 vector as a solution. But you can only do this if A is regular. Is A regular in our case? No, it's singular. And what is the condition of singularity? Yeah. If for instance you have two rows that are proportional, then it's singular. Another way of saying it is that the determinant is 0, and it is in this case. So lambda equal to 0 is an eigenvalue. Now, maybe I jumped to this conclusion because if you look at it, you have proper solutions to this equation here if lambda is equal to 0. And this is the condition. Then the eigenspace corresponding to lambda is more than the 0 vector. So it is because the dimension of the kernel of f is greater than 0. Okay. Let us look at, now I'm just trying to guess an eigenvector for this problem. And you can see that if I guess 0.0.1, then there will be no contribution when I make this matrix vector product from the first two columns, only from the last column. So if I do this 1 minus 4, 0, and 0, 0, 2, and so my claim is this is probably an eigenvector. So I do the matrix vector product, and I get 0, for the next line 0, and then 2. And this is 2 times. So yes, 0.0.0 is an eigenvector with the eigenvalue 2. See here, you have here the eigenvector. So I have one eigenvalue, I have two eigenvalues. Now I'm going to tell you, yes, it is a sentence, but lambda 1 plus lambda 2 plus lambda 3 is equal to the trace of A. Now, what is the trace? The trace is the sum of the diagonal elements in a matrix. So this is a general identity for eigenvalues of a matrix. So the sum of the eigenvalues is equal to the trace of the matrix. Now, I have one eigenvalue here, 0. I have an eigenvalue 2 here. And what is the trace of this matrix? It's 1 minus 4, that is minus 3, plus 2, that is minus 1. So I have that this is equal to minus 1. So I have that 0 plus 2 plus lambda 3 is equal to minus 1. Then lambda 3 is equal to minus 3. Okay. Now I have three different eigenvalues. I have 0, I have 2, and I have minus 3. And that is, I have three different eigenspaces, and I have, when I put up this theorem here, so the eigenvectors of different eigenvalues are different. So or are linearly independent. So now I have three linearly independent eigenvectors, and I have a 3 by 3 matrix. So yes, it can be diagonalized.
How did you arrive at the vector 0, 0, 1?
I guessed it. You're not supposed to do that. You could have calculated it, but you look at this matrix here and you see you get something simple if you choose this vector, because then you only get contributions from the last one, and you see that the last one has 2 zeros and then something different from 0. So this is what you try out, and it works. But you shouldn't rely on guessing too much. I will show you how to do it the hard way. Okay, I can sharpen this theorem here, and I can call this theorem 3, and I think it's 14.8 or something in the e-notes, but it says that if A has n different eigenvalues, then A can be diagonalized. Because by this sentence up there, if it has n different eigenvalues, it will have n linearly independent eigenvectors, and hence it can be diagonalized. I will take a break for, say, 5 minutes.